Thanks for arranging in such a short notice, and sorry to force kind of stop a seminar at this particular time. So I'm going to, as announced, I'm going to talk about uh, contact convexity. So just very briefly,
you're entitled to take off your mask.
Oh yeah.
I am flying.
You're
I don't want.
entitled to keep it on.
Yes, but I'm traveling on Thursday, and this guy are kind of crazy on.
You don't want to take any chance.
Yeah,
That's a good attitude.
otherwise I can't. I hope you don't mind. If you can't hear, I'll remove. So you have this contact manifold, and we have a hypersurface. And let's just very briefly recall what you mean by a convex hypersurface. So you need basically two notions. You need the notion of contact vector field for this. So vector field on M is called contact vector field provided the flow provided the flow of this vector field preserves the contact structure. That is flow of X preserves contact structure. And once you have this notion of contact vector field, one can say as such. So if there exists a contact vector field S transverse to a sigma, say sigma is contact. So the thing is that because of this transversality, it gives nice contact neighborhood of this surface. So of course, notion of convexity is extremely important. I'm not going to go into it because probably there are experts who can say much more than I can about it. So I'm just going straight to the question and what can we say about making surfaces convex? So the question that we'll discuss is, can make any sigma convex by a C0 small what is known is that this notion is due to Giu, and he in fact proved that in dimension 3, that is when manifold, any closed surface is C0 close C infinity close to a convex surface. So, well, such thing is certainly not possible in higher dimension, but we are now going to only look for the whether it is possible to produce LC0 small perturbation to make surfaces convex. And the what the reading seminar was about was regarding the paper of Honda and Huang, which claimed that in fact it is possible to make this approximation. So the way in which they approach this problem is okay. So let me just state the theorem. There exists a zero small sigma to sigma tilde such that sigma tilde is convex. And the way in which they achieve this is by manipulating characteristic foliations. So let me very briefly review that also. So we have, so you recall we have data which is sigma, the 2n-dimensional surface inside some contact manifold, which is actually kernel of form alpha m. Then I can define a form beta, which is this form alpha m restricted to sigma, and generically at the generic point beta is non-zero, then one can look at kernel beta at this point, and d beta will then have, so let's say kernel beta, and at this point there is a line field L, so that d beta is equal to 0 for every v in this line field, and this line is called this defines a singular one-dimensional foliation on sigma, which we would call characteristic foliation. So yes, defines singular line field sigma, which we call characteristic foliation. Notation for this is okay. So the place where this line field is not defined is precisely the place where the kernel of alpha is tangential to the surface. This follows from the condition. So now given this characteristic line field singular, any vector field on any vector field tangential to is called a characteristic vector field. By defining this kind of vector field to be zero at all the points where line field was not defined, you can actually define a vector field on whole sigma, which has value zeros precisely at where the points where there is a singularity of the line field. Okay, so I'm not going to kind of go into detail of this, but if you put an orientation of sigma, there is a natural way to orient also this vector field. This is not very important for our current purpose, but just for the sake of understanding, you have this surface, and in the 3 dimension, this line field is very easy to see. You just take a contact plane and it's going to kind of intersect my surface in either one-dimensional line, or the contact plane is going to be tangential. So points where it is tangential is a singular point, and other points it defines the line field. So this is my characteristic position. So you can reformulate the notion of convexity, and you can write down a certain criteria on the characteristic foliation that would guarantee convexity. So I'm going to kind of just write it down. What does convexity mean in terms of characteristic foliation? So this is this and this particular what I'm going to do is proved in all is kind of sketched in reasonable detail in the article we are discussing. So I will not kind of go to the proof of this criteria. So our surface is convex if let's just go back. So we have m, psi m, and sigma, and V is m characteristic vector field. Now, suppose there exists V is m such that all singularities of V are of most types. So here again, I'm assuming that slightly abuse of words, but by most type here means it's kind of locally pseudo gradient for some Morse function. So whenever there's a zero, there's a Morse function, and this vector field is a pseudo gradient for it. And I'll be right here. So first condition was conditions. First is singularity. Right. It is actually a very mild condition. You can always achieve this by perturbation. So we won't focus on this. This is kind of, let me just write down here. It is doable without going through the more technical aspects of this article. But the second condition and the third condition that I'm going to write is quite non-trivial. So for the flow associated the characteristic vector field, omega limit alpha limit of any trajectory the singular point. You kind of cannot have, which is most natural, is that if the condition currently is like you cannot have a trajectory that kind of ends in some periodic orbit or does some funny things. Everything kind of limits into a singular point. So this is, of course, as you know, kind of very strong condition. And I would add something is that there is no trajectory which connects two singularities of index K and L with there is no connection between you in the 3 dimensions is kind of difficult. You have some singularity like this, then there is no connection between this. So every time there is connection, you will kind of break it by introducing something which is a sink and so I'm not precise at this point, but essentially you don't actually prove this. You just prove that there is no what is known as broken loop. It just means that you don't have if I am allowed to travel from infinite time, I'm not supposed to come back to the same point I kind of started with. So there is no like it's a loop with singularity on it, and there is a direction, and I cannot sort of come back if I allow to travel infinite time. So there is no such loop. That's what you need in the criterion, and that's what I will focus on that.
What do you mean by omega level?
I mean, you start from here, either in positive time or negative time, you end up with some singularity. That's all you keep in mind. Okay. Take any point and you travel in forward time to some singularity, in the negative time of them. Yeah, but here is very simple closure and that's condition. Okay. Okay, and there is and there is an additional condition which says that there is no retrograde connection, but I'm not going to go into this. Actually, you can give some signs to this singularity because of the existence of context structure, and you should not be connecting opposite sign singularity. But that condition again is mild because it can be achieved by C infinity perturbation. The most hardest thing to achieve is condition number 2 and 3. The technique for achieving both of these is similar. We just kind of any orbit that is limiting into some bad set, we stop it and force it to enter a singularity. Okay. So let me
is that like the mushroom plugs? Is that what they're used for?
Yeah, mushroom plugs are for that. Yeah, I'll come to that. Now I'm going to. I was very fast because I wanted to just.
But if you would write everything down, then this is equivalent to convexity, if we can achieve all this.
If you achieve all this, then it is equal to convexity. This is sketched by them in the article. It is that's not a serious problem if you can prove it. But essentially, if you look at the proof given in Jihu's original article, it's very clear and you can kind of generalize that. So it's basically, I would call it Gibbs criterion. So that part is standard. So can I go ahead? Okay. So just keep in mind that you would like to modify you would like to re-embed my surface in such a way that the dynamics of the characteristic foliation satisfies the condition 2 and 3. Okay, that is the key thing we have to keep in mind. Okay. So the first condition you just achieve by a small perturbation, and without disturbing that you can achieve 2 and 3. That is what is the goal of now the discussion is. Okay. So let's just have so let me just write preliminaries. And the first notion we need is what is known as transverse contact. So the data we have currently is we have sigma, and as soon as we have sigma, we have an induced characteristic foliation. And the task is to kind of change this to some sigma tilde, such that this characteristic foliation on this is satisfies those conditions. So here is, so as I told you, the given sigma, we assume that all singularities are almost right. This is just achieved by a small perturbation, by just making things non-degenerate. So this is expectancy. Now, there is a theorem by Wilson which says that you have a, let me kind of draw it and then I will write that. So you have some piece and you have some singular foliation. You have some singular foliation connecting various things. The theorem of Wilson says that you can find a collection of transverse arcs which are disjoint from this singular point, and such that each leaf comes and hits at least one of the arc in its interior. Okay. In this two-dimensional case, it is arc. If this is higher dimensional, then this arc is replaced by a disk of corresponding dimension, dimension 1 less than the. So whenever you have a singular characteristic foliation with this most type of singularity, you can find a collection of disk such that each leaf, each trajectory hits one of the disk in the interior. Okay. So this theorem implies there exists a collection one T2 TK of closed balls each is of dimension 1 less than the dimension of sigma. So there is a collection of closed balls which satisfy the following. people who are kind of reading, who has tried to read this article, I would just like to point out that from now on, we are just completely changing the strategy of the proof. I mean, we are following general philosophy of the proof, but we are trying to present a simplified version. Okay, so there is this collection of closed ball, so that first each leaf needs interior. Alpha M induces the contact structure on sphere. Now I cross D2, which are transverse to my
This alpha M.
alpha M is I'm always
Alpha M. Yeah, sorry, I was reading M. Okay.
Sorry,
Yeah,
sorry.
good.
my handwriting. I'm trying to write fast. So
Yeah, that's good.
it's the same. Always alpha M, M and sigma is fixed for our discussion. So this alpha M induces basically standard contact structure on the ball. And these balls are transverse to the characteristic foliation, and every leaf hits this ball. And this is just follows from this result of Wilson that I have quoted.
So, you said what happens at the boundaries? Boundaries,
There is no boundary, it's a closed surface.
right? But the boundary of the balls.
So this is, foliation is already transversal to it because these are standard singular, most singularity. So I just neglect them. Currently, I don't care about it.
I'm trying to picture how. So the boundary of these TIs are supposed to intersect, for example, the boundary of balls around the singularities.
No, they are in the. We don't even bother about it. We forget about this manifold. We just remove these balls from it. We forget about what happens to that foliation. We are just looking at the now non-singular foliation on the manifold, and then we construct this collection of balls. I can quote I'll give you the more detail about this article. It's just direct consequence. We remove the singularity and so you have non-singular foliation, and to this you have a collection of once you have this manifold with a boundary with non-singular foliation, you find this collection of balls. None of them hits the boundary.
Are those TIs disjoint from each other?
Okay, so I have lost the order. Okay, let me keep this up. Okay, that is better. All this, so there's a second condition. The third condition is that of course they are disjoint. And the fourth condition is that of course it's a consequence of the contact structure units. there is a neighborhood UI of TI such that alpha is given by and there is a standard neighborhood of all this. So leaves, I forget about the singularity and I kind of look at the small flow box region of this foliation, and then I can apply some standard Darboux kind of method to produce a standard neighborhood up to contact homomorphism. This is all up to contact homomorphism. The contact structure is given by this, and this UI is a neighborhood of those disks. So you can think of this UI as a small R2 times Ti. Okay, so remember that. Okay, so now let's go to the step 0. So this is our preliminary. So I'm going to kind of quote this theorem and assume that you always have this condition that you have a singular foliation and you have this transverse collection of balls and your leaves are hitting this interior of this closed ball, at least one of them. Okay. Now the idea is that you kind of do a perturbation of this ball, give a re-embedding of this ball, which is, or rather ball times I, you give a re-embedding such that the boundary remains same, but dynamics, the characteristic vector field changes, and things that was entering actually goes inside a singularity inside the Ti cross. Okay.
Wait, so for each leaf, you're going to have one of these broken leaves, those leaves, or
no, right now I have just, yes, no, I have just looked at all singularities and I have just produced some collection of balls such that you take any point and you kind of travel along the flow, it will hit one of the Ti.
okay, so each
in the interior.
Or in the whole thing, any leaf.
What?
Like, each leaf meaning all the leaves of the
Yes. Every leaf hits at least one Ti in the interior. Sorry, is it clear? Okay, so let's see how to do this in the 3 dimension, though it is of course.
So then when you write that each leaf meets Ti in its interior, so you
Oh, no. Some Ti, sorry.
some Ti, yeah.
For some I. Just trying to write too fast so that I go to the main part. Sorry. For some I. Maybe that was the confusing. Yeah. Sorry about that. Already more than half an hour, and I have not yet come to the meat, so I'm kind of thinking. Sorry about it. Okay. Is it clear? So step 0, as Honda will say, grow mushrooms, is that we want to kind of, so remember that, so I will kind of explain this just via picture. So remember that in this, you have this foliation and this is your Ti, and the foliation is kind of going transversely hitting this Ti, and and we kind of change this foliation so that following happens. Okay. So there are many ways to prove this, that you can find a C0 approximation of this region such that when you produce this C0 approximation, of course the new region has the same boundary as the old one, and now the characteristic foliation on the new region looks like this. Now what are the properties of this characteristic foliation? First, that everything, almost everything except the small neighborhood here kind of enters a singularity, so gets blocked. Okay, so it doesn't allow it to pass without hitting the singularity. But second and most important thing, that of course things which kind of enter here and exit here, they don't exit, they exit in a extremely small neighborhood of the point where you entered. So if you project it back, there is a natural projection here, and you mark the entry point and you mark the exit point, and they are arbitrarily close. Given, you can make them arbitrarily close. That's the whole point. So basically, this means that when you insert this, what we call plug, you don't disturb the dynamics much, but you achieve this property that you force the flow lines to kind of turn and enter into a singularity everywhere, except maybe in a small neighborhood near the boundary, where it enters and exits with absolutely close to zero change in the, let's call this as T coordinate. Let's call this S coordinate. Let's call this T coordinate. Then in T coordinate, if you measure the entry point T coordinate and exit point T coordinate, the difference is very small.
That's what it was transverse to sigma. I'm just confused.
No, the characteristic foliation is on sigma, and the T, this line is my Ti, which is transverse to the.
So
Yes, but is this picture in sigma or where is this picture?
This is picture in sigma.
But S is 0 on sigma.
That's
I'm
what I'm saying.
also confused.
I think you're using the same letters for different.
No, sigma is given by coordinate Z, T,
No.
R, and whatever. This is the coordinate of sigma.
Yes, but you're drawing an S coordinate.
Ah, okay. I just wrote to explain that. Sorry, that's not S coordinate. There's a chord. So this is some T coordinate. Let's call it some other coordinate. I don't know. Z, P. I was just explaining that there's a coordinate. There's a direction given by the flow. If you wish, you can change this. You can equivalently write this as Z plus some lambda, and I can take Z equal to 0, whichever is convenient for you. In this case, I can take S coordinate because the characteristic foliation is given by d by ds. So you can take this neighborhood if you wish. Yeah.
This I find even more confusing because I thought that is the coordinate of T of Ti.
Okay,
That's it.
But
now you are happy. What I want to say in the coordinate is the following, that you have this transverse R and my surface is given such that this is the characteristic foliation. So I can keep this as a, say, direction as, so now I'm writing here in this direction, I will write this as e to the power S, which is my Z direction. So I should remove this and put Z here. And now I want to replace it by this picture, which I kind of drew. Now is it clear? Just choose a neighborhood that is just choose a coordinate neighborhood that is convenient for you. Standard contact neighborhood. Now, can I go ahead?
It deviates, so if you're near the boundary, it exits there.
Yeah, if you are near the boundary, it exits
Then
almost at the same point as it
yes.
exits.
Then you go closer to the singular points which you have, and you just say it.
Yeah.
So up to where does it change very little?
So from here, it kind of, okay, let me draw here. So very close, it's actually, here it's actually identity. And then in this region, so in this region, it kind of goes like this. It follows this and kind of goes inside this. So this thing which connects this hyperbolic point or everything on this side of hyperbolic point, it kind of forces it to go inside. That's the picture.
And you achieve this by changing sigma in C0.
Yes, yes, you achieve this. I mean, they achieve by putting what they call mushroom. But you can just do the following. You can just take this flow and then just first create a kind of standard procedure of pair of kind of cancelling pair. And then on this hyperbolic, you can produce one of these trajectory. You can again add a cancelling pair, and you can take this picture and apply a appropriate diffeomorphism so that you are kind of forced to turn and enter in this area. So up to a diffeomorphism, it's just adding a pair of cancelling singularities. Okay. But this part, like in the article, they have clearly explained that how this dynamics changes and what is the perturbation. So they basically, if I denote in one dimension surface like this, so this was my like, I'm coming like this, they kind of replace it by something that looks like smoothen version of it. Okay. So therefore, this property is satisfied by this perturbation. Yeah. Can I continue?
Dishant, but this like it's not quite C0 small. This it's a perturbation of the size of the square, right? So it's kind of like a
yes, but it's done along a very small scale square.
Yeah, yes. Yeah, but okay. But if square is kind of fixed, you cannot make it arbitrarily small.
Yeah. Okay. So now you know where to direct the question. So this is the kind of zeroth step that in 3 dimension you can kind of do this particular picture and achieve, you can kind of block. I'll come to it. So the thing that what you want to do in higher dimension is naively, you think of your, whatever, this Ti cross R2, which I denoted by Ui, whichever contact form you want to choose. But you can think of this as like, I have this, there is a base Liouville domain, which was like, remember it was I cross D2 and was some standard contact structure on this. And this, so there is like a three, you can think of that as a kind of fiber bundle, which each fiber is a contact 3 manifold. And your surface is just a surface here times this D2. So you can kind of achieve something like following that sigma intersecting with U looks like some sigma 1 containing R3 times you see here. is the two-dimensional part and this is the three-dimensional part. And sigma is like some surface here, which is given like this, times d2 coming from this factor, okay? And naively, what I would like to do is like, so in this picture, we would like to kind of change each fiber by the three-dimensional perturbation that we have achieved. And of course, there is an obvious problem that you can keep this as a three-dimensional perturbation. In each three-dimensional, you can do this wiggling. But when you come back, when you come near the boundary, you have to again undo this, and so that you can glue back the things. Okay. So there is the and now after achieving this three-dimensional case, you can divide your five-dimensional cube into kind of two boundaries. One boundary coming from the three-dimensional part and another boundary coming from the two-dimensional part. And that three-dimensional part boundary is of course kind of taken care, because here we have preserved the boundary here. But when we want to kind of go near the boundary of this D2, we have not sigma but a perturb sigma. And so we have to kind of undo all the things that we have done as we go radially out along this D2 direction. And that when you do, you realize that it actually all the good properties, I mean this good property that you enter here and you remain very close when you exit disappear. Okay, so one has to kind of come up with a technique to control that. So that is what is the main point, which I will try to explain now.
So what is in this Honda paper? Is that still, are you doing something new here?
Huh?
In the Honda paper,
Huh.
Is that still there? Or?
Yeah, this part is clearly there, but the higher dimensional part is where this, what I'm explaining, that you want to kind of do this fiber wise, and then you have to come to the boundary and glue back, so without kind of making foliation, without changing, with having property that near the boundary or not may disturb the flow line so much. That part there is an issue. Okay, so so here is some property you can calculate. So remember that we have some five-dimensional ball, and inside this, the sigma intersection U5 is just some sigma 1 cross D2, where sigma 1 looks like with a coordinate, what is it, Z, and there are some coordinate and P direction. This is the flow direction, and we have this picture. So you have like your starting point is parameterized version of this square. Each point over D2 has this square, and this is the foliation one. And you replace on each point by this picture and try to control when you go near the boundary of this D2 to come back to this picture. Okay. And when you kind of do this, the procedure that I told, describe, that you get the following. So this is your TI, and I want to kind of understand what happens to what happens near the boundary when install this plug, parametric plug. calculate what happens when we go near the boundary of the disk by looking at this Ti, which was I cross D2. And you can see by explicit calculation that this is my, so this, let me put now parameter here. This is Z and this is D2. And you can see that close to this endpoint, you have a always a movement. As we enter this block, we exit with a movement, which movement is controlled by the characteristic foliation on this D2, meaning the Liouville vector field of this D2. Remember that this disk is a disk with a Liouville form on it. Okay, so here it is controlled, it is governed by Liouville field. On the top, it is the precisely opposite of the Liouville field. So we have a directionality. As we try to put this parametric family, we have a directionality which follows the Liouville vector field on the top and follows minus of the Liouville vector field, follows the Liouville vector field on the bottom and minus of the Liouville vector field on the top. And we have completely unknown dynamics in this region. We don't know, except that we have a directionality. That if a particle enters here, then it exits, and if you measure its height with respect to this Z coordinate, then it is at least either bigger or same, but it's never less than that. So there is a directionality that you enter here, you follow this Liouville field, or if you are in this region, then you go up, but you don't go down. So there is a directionality which you can calculate.
But probably you will not use it anyway, right?
But this directionality, I just want to motivate that if there is directionality, you can put the two block in such a way that you can kind of go along this direction, along the boundary direction.
Okay, but for your purposes, that you can do without it. It doesn't really matter, right?
Yeah. Okay. Okay. So here we have kind of no control. What happens? Like in this, it follows negative Liouville, and here it follows the Liouville vector field. And now what we do is okay. So first, so we take this Ti is equal to I cross D2, and by installing enough plugs on boundary of I cross D2. Remember, this is now three-dimensional contact manifold, the transverse thing. So its boundary I can make convex by applying the 0th step, because it's a three-dimensional manifold. And in fact, we can make the dynamics, make the boundary epsilon short. By which I mean, okay. So let's just schematically.
Epsilon.
Yeah, I'll
What is the next one?
short.
Short.
I put a Riemann metric on this, and I find an embedded. I can kind of put up the boundary. So let me just draw the picture. So you have this. This is your cylinder, and I replace it. I mean, I find inside this near the boundary a new kind of boundary that encloses my cylinder and is very close to it, so that on this new boundary, if I look at the correct characteristic foliation, I can only travel. Every leaf has length at most epsilon. So I kind of keep dividing my. I not only achieve that property, but I actually further achieve a property that allows me to not travel at all in some sense. Given epsilon, I kind of, within that time you hit the singularity, okay? With respect to some auxiliary Riemannian metric on the whole surface. This can be done by just modifying step 0 slightly, meaning you don't find an optimal collection of Ti, but you can keep adding Ti till you achieve this property. And now the last step is the following. Then I'm going to draw that crazy boundary and just simplify in the following way. We have this. I'm going to draw ball as Pi because it is I cross this. So you have this boundary which I call it W plus and W minus, and it has a dividing set. This is these both are Liouville domain, and this is a set along which the orientation induced by contact structure kind of changes from positive to negative. And what you do is you can kind of produce a sort of Wi cross. This is your W plus cross I, and in this picture this is the region where we have no understanding of the if we install the plug, if we do the procedure I have done on W cross I, then we have no control what happens near this red line. And similarly, you can kind of get another side. And this is W minus cross I. And these regions are the one where we have no control over dynamics. And then, but we use the fact that, notice that if you have a dividing set like that, it is a very standard neighborhood and its characteristic foliation looks just straight line like this here when you restrict to this particular place. So using then the trick is to kind of find a standard this is a standard Liouville disk embedded in this region, which has a standard Liouville disk, meaning if I restrict my form to this particular, it just looks like R square d theta. So inside this W cross I find a Liouville disk like this and another one like this. And this is possible because essentially you do undo the things you have kind of done. So you produce, in this way you can kind of find two disks, D1 and D2, such that on this D1 and D2 the characteristic foliation is just standard one. So on first disk, there is a disk here and the foliation on this is standard, and there is another disk where the foliation is standard, except that of course they have kind of, they are glued by the opposite orientation. And so you can find a sphere inside your TI where it looks like a standard sphere in the standard contact 3 manifold. And since the contact 3 manifold is tight, you can apply Eliashberg's classification of balls and ensure that everything in the interior is the standard contact ball. And so this particular white circle is actually contactomorphic to I cross D2, and such that the bad region of this I cross D2 is kind of lies here somewhere very close to the dividing set. Because every block that you consider has a bad region, but it kind of lies in the so this construction allows us to construct 3 blocks such that all the bad region of first block is in the interior of the blocking region of the second block, and bad region of the second block is in the interior of its anything that comes to bad region of the second block is already coming from something which was blocked. And then the third region also has this property that anything bad that was dynamics which had no control was already blocked. And so after putting these 3 blocks, what you achieve is that everything, more or less everything that enters this ball is blocked, and things that exit this block follow the characteristic foliation of this boundary. But I have already ensured that this characteristic foliation is epsilon short by previous step. This guarantees that when I exit the ball without getting blocked, I am not moved much. And so you have not disturbed the dynamics so much. And this kind of produces, these 3 blocks put together produces all the properties that you require for the standard 3-dimensional block. So that's the idea.
Okay, thanks.
There will be a paper explaining this. There will be a paper explaining this.
We are writing. Just the last part needs to be explained. Other things they have worked out correctly.
More questions? I guess we are waiting for the paper.
So how long will it be? Sure.
Ask Yasha.
Yasha?
We'll try to do it fast.
Yeah, fast, but how long will it be?
That depends on the font.
Before the summer.
Yeah, how long will the paper be?
How long the paper be? Okay, but I would say, okay, 30 pages with preliminaries.
Okay. Looking forward to it.
You can do it in any dimension.
Yeah, you can do it in any dimension, yes.
But then I am not checked, so I won't say. Here we are using this in putting this second block. We are using the characterization that your standard sphere and inside there's a type constant is unique.
But it's overkill.
Yes, but yes, it's overkill, as Yasha says. But so in 5 dimensional, it's completely clear that you can do it. Otherwise, you have to kind of undo this thing carefully. And Yasha has written down something, but we have to check.
Very well. So thanks.